So, game theory applied to the blockchain. So, first introduced by IT engineer Stuart Harber and physician W. Scott Stornetta to protect important data, the blockchain was rapidly proposed to serve as a cryptocurrency transaction ledger and is currently widely adopted for a large number of cryptocurrencies such as Bitcoin, Ethereum, Ripple, and EOS. The blockchain can be defined as a distributed public data ledger maintained by achieving the consensus among a number of nodes or players in a peer-to-peer network, which will be explained later. The verified transaction data is stored in a chain of blocks, which are the basic structures of the blockchain. So the rational nodes perform action or strategies that aim to maximize their own utility, but they can also launch attacks that damage the blockchain. To protect the blockchain, we need to address security challenges. However, the blockchain network is a large and decentralized system, so we cannot use a consensus protocol such as the Byzantine model because it requires a centralized permission controller. Thereby, conceptors of cryptocurrencies, and especially Satoshi Nakamoto, the conceptor of Bitcoin, considered a game theory to analyze the strategy of consensus nodes or block miners and their interactions. So, to give a quick definition, the game theory is a study of mathematical models of strategic interactions between rational decision makers. A key objective in game theory is to identify equilibrium outcomes, particularly the Nash equilibrium, where when no player can benefit by unilaterally changing their strategy. So in the case of the blockchain, it can help block miners to learn and predict mining behaviors of others. And so they can have an optimal reaction based on equilibrium analysis. And it can also develop incentive mechanisms to discourage block miners from misbehaving or attacking the blockchain.
Now we'll look at application of game theory for mining management. So, which is an example of using game theory in Bitcoin. So to create a block of the blockchain, nodes, so miners are working toward a consensus mechanism to verify the transaction, which is a proof of work mechanism. It allows simple and secured transactions. So concretely, what are the players doing? They are trying to solve a complex mathematical problem, which we will call a puzzle, and actually what they are to add the next block to the blockchain. So concretely, they are looking for a hash, which is the result of a mathematical function. In Bitcoin, it's SHA-256, which computes a unique output for each input. And why are they doing it? Because the first player to solve the puzzle is rewarded with cryptocurrency. They have a condition, which is that they need the previous hash. So they need to solve the previous puzzle or to have the previous puzzle solution to start looking for the new hash. So to continue the chain. But so there is a choice once they have found the hash, so they have resolved the puzzle. Miners can choose either between reporting directly the puzzle, which is so earn directly the mining reward in cryptocurrency, or not report / keep looking for the next one before others do. And this is so a selfish mining attack was a type of subversive strategies in proof of work mechanism based on blockchain systems that attackers may not broadcast the newly mined blocks, but choose to withhold the block. Why? Because if they do so, then they can start to look for the next solution of the next puzzle before others do, which gives them an advantage over others, which then use their power, their hashing power for nothing. But the problem is the miner who has found the solution to the puzzle may not be the only one. So there may be another miner who has also found a solution. And then we have a fork, so two different solutions to the same. And then there is the problem that other miners can decide, must decide on which solution to continue mining, so on which chain to attach its block. And so if miner 1 had the solution, but decides not to reveal it, and miner 2 gets reveals it, then and other miners choose to be on to continue mining on the second player's solution, then miner 1 won't get any reward. So this is the problem between reporting or not reporting. However, the goal of the blockchain is to be the longest possible. So the goal of the Bitcoin itself. So it has for the blockchain, it's better if players are honest and report the puzzle, so we can create the longest blockchain possible. So we need to create an incentive to players to be honest, so to report slash this is rewarding information propaganda. Indeed, if only one miner at a time works on finding the next puzzle because he doesn't want to compete with others and get the best reward, then it takes a long time for him to solve the puzzle if he's alone, as if all the miners are working on it. So it slows down the blockchain principle. So the fork chain selection is a sequential game with imperfect information, as we have found it. And we have many variables. So we have R, which is the puzzle to solve. We have V, the price to solve the puzzle. We have HI, which is the hashing power of I, and also the probability that I is the first to solve the game. And alpha, the probability that players J and K, so players 2 and 3, choose to mine on top of the solution that I found. So this is, as we said, a sequential game with imperfect information. So, for example, let's assume that miner 1 has finished the first puzzle. He believes with a probability of H1, as we saw, that he was the first one in doing it. So if one chooses to report, then he immediately, this is on the branch at the left, he immediately collects a reward for the first puzzle. In this case, all miners start the next puzzle simultaneously, and since it's the last puzzle, since we're in a two-game puzzle, two-game sequential game, its winners announce his victory as soon as he finds a solution and gets the corresponding prize. So in the end, either H1 gets 2 and the other 0, or he gets 1 and the others have either H2 has 1 because he won the second game, or H3 has 1 because he won the second game. And the other H2 or H3 has 0 because he won nothing. Or alternatively, so he chooses not to report and starts working on the next one. But then if one is first to finish the second and last puzzle, which occurs with probability H1, so corresponding to his hashing power, he's rewarded with both prizes, as we saw, 200 and the end of the bunch of the left called H1. But however, it may be the case that one of his rivals finishes the first puzzle before one finishes the second one. And in this case, with probability H2 or H3, but I will talk about 2 because it's more simple. So 2 finishes the puzzle and also has to decide which action to take. And if he chooses R, then H1 also chooses to publish immediately in order to compete. So this is the fork. And then with a probability of alpha, other miners will decide either to work on the solution that one found or on the solution that two found. And so this is alpha. And in the end, if one finishes, if miners select the first one solution to continue mining, and one is the wins also the second game, then he has two. But it's the same as before, and if he doesn't win the second game, he has only one. However, if they decide to mine on two, then he could get 0 even though he found the first game. So instead of having 1, he gets 0. Here it's the same with also with others, with other, in the case where miner 1 believes he's the second one. So after miner 2 to finish the first puzzle. And then, so we have to, in order to get the Nash equilibrium, we have to compute the expected payoffs of each, the expected utility of each of these players, but we focus on player 1 in this paper, which are written here and are according major to the hashing power, the probability alpha that people will choose to mine on the solution that the player 1 found, and the probability that player 1 thinks he's the first one to have solved the game. And then we need to, so this is for the action, we need to calculate this expected payoff for the action of reporting and for the action of not reporting. And as we can see, game theory helps us here to understand Bitcoin because player 1 will play according to other players' hashing power and other players' beliefs that they have found the solution to. Then, thanks to the definition to the expression of the probability that player 1 or player I believes that he is the first to have found the solution to the puzzle, according to to the belief of other person, hashing power of other persons, and the beta, which is the probability that other people will choose to not report a solution if they find one. Then we can compute, and we have the probability that miner I chooses to not report with probability beta equal 1. So if it's true not to report, if and only if hi is superior to this, computed from the expected utility which we saw before. And so this gives us, with those two examples here, we found out that it is enough for the miner I to have a hashing power of hi equal to 1/3 in order to not report. With different conditions, like with alpha equal 1 or alpha equal 2/3, or with other conditions like the value of the beta of other players. And so in the end, the miner will not find it optimal to report if his hash power is below 1/3. So in conclusion, not reporting is only an optimal strategy under certain conditions. So there are many Nash equilibria in by induction, which can be found in the previous sequential game that we saw. But it's so it highly depends on the parameter alpha and also the parameters of H. But if there are three miners, I will report if his hashing power is below 1/3, so the blockchain has an incentive to make it that. However, there are limits to this explanation. First, all players are considered rational, which is not always the case. Second, this is a two-stage game, although in Bitcoin the proof for puzzles is infinite, so it doesn't stop after the second game. And finally, the cost of using hashing power is considered as being equal to zero, which in reality is not the case. Using hashing power costs something to the player.
We have seen a detailed application of the game theory in the blockchain. However, there are plenty of application of the game theory in blockchain. So here we're going to focus on rapid application to other mining management models, especially the computational power allocation in individual mining. So first of all, what is computational power? So it is the ability of a system to perform complex calculations and process data quickly. So first, each miner needs to determine whether or not to invest in computational power given the other miners' strategies. In this case, we can use a non-cooperative game as it is a competitive environment. Thus, a unique Nash equilibrium exists at which investing is the best response of each miner as long as the miner's computational power satisfies a condition. So, the condition here is determined based on the computational power and the marginal cost of the miner and the entire Bitcoin network. However, there is another theory concerning allocation of computational power, where a miner can choose between investing, arrival, or leaving the mining, departure, at any moment of the game. So most of the time, miners' strategy depends on the number of miners participating in the mining, given others' strategy. So in this case, we could apply a stochastic game to analyze the miner's strategy, and we could find the solution in a sub-game perfect equilibrium, which is a basic response when facing sequential decisions. In this case, the miner's utility is a function of the number of the miners in the system, of course, the arrival and departure rates of the miners, the rate of proof of work getting solved, and the cost and the reward of the mining. So after this, the player must acknowledge the amount of computational power that he is ready to invest to win the minimum rewards. So thus, using a chrono game enables the analysis of the interaction between the miners again. Here, the solution would be again a Nash equilibrium, showing that the average revenue for the miner to invest in a unit of computational power is equal to marginal costs. However, it is also interesting to consider a case where the transaction fee is superior to the mining reward, which was not the case in previous theories. So here, miner would need to adjust its allocation by choosing the proper time to start mining. Miner have miners have no incentive to mine unless the accumulated transaction fees sufficiently exceed a certain threshold. In this case, we can use a non-cooperative game to analyze the interaction among the miners. Each miner's utility is a function of the starting time, the operation time, the proportion of the miner's machines, and the probability distribution function of the block finding time. So this experience from Sabari and Eol has shown that the miners that own the same number of mining machines eventually converge to the same starting time, meaning that the game reaches a Nash equilibrium. So a lot of other models, such as auctions, are used to understand mining management, but we can not talk about all of them. So let's go to the conclusion now. Through this video, we have seen that game theory plays a fundamental role in the blockchain, ensuring security and helping understand the node's behavior through the conception of blockchains.